much for coming. I appreciate the opportunity and invitation by many institutions, including my colleague, Chris Monroe. I'm going to tell you a little bit about our mainly a big collaboration we have with Chris and others on trapped ions, mostly but on the engineering aspect of how do we put things together with new technologies to try to build a quantum computers or quantum communication systems that people have been talking for a while. I'd like to lay out a vision and our technological approach to hopefully realizing that vision. So I will start with an introduction of a very brief introduction to quantum information processing. Maybe there's half of the crowd understand that very well, but maybe not for the other half. But I'll do it in a way that we extract the very operational essence of it. For example, when people are doing circuit design in classical chips, they need to understand how the transistor works. But they really don't have to understand the details of how the transistor works. They just need to know what it does. And there's if any of you have read this Art of Electronics book, there is the transistor man, right? That's what the circuit designer needs to know, what the transistor function is. So I'd like to basically abstract the quantum side of it at that level, and then really think about what are the engineering aspect we can aspect. So we can concentrate to make the systems work. So I'm going to try to cover that in the introductory part. And then I'm going to show a couple of vision of how we envision to scale this to a much larger systems. That can either do a quantum computing platform called a project called MUSIC, or a quantum communication protocol platform that we call Spark. These are two collaborations that are fairly large collaborations that I share with Chris. And then I'm going to really then focus down onto the technological aspect of what we think can be done using new technologies that are currently under development. So if you look at any classical processors that you have, the most significant example is these things that are in your pockets today. There is a lot of bits that are being processed, and they are always represented by a physical system, whether it's a charge state in a transistor, or a magnetic domain in a hard disk drive, or an optical pulse in an optical communication system. A bit is always represented by a physical system. And all of our information processing systems are represented by basically classical physics. But we know classical physics is a subset of quantum physics, so if we allow quantum effects to take place, can we do more interesting things than what classical laws of physics allow us to do? And the answer turns out to be yes. The first discovery was quantum communication. People figured out that if you truly use the quantum physics and use individual quantum systems to communicate information, you can actually do fundamentally secure communication that is that nobody can eavesdrop. An example of that is quantum key distribution. And then the other aspect of it is if you allow the superposition principles and entanglement to persist in your system, then you can come up with quantum algorithms that solve certain problems much more effectively than any known classical algorithms. And a great example will be Shor's factoring algorithm or Grover's search algorithm. So just like classical computers, in classical computers you need physical systems that represent bits. And then we need processes that allow you to do logic operations between the bits. And so similarly in classical physics, in quantum computation, you need qubits, quantum bits, which is a scalable set of two-level systems, quantum systems, that represent the quantum information. And this can actually be both in 0 and 1. These are two quantum states. But quantum mechanical laws allow you to create linear superposition of these states. And if you have more than one such qubits, then you can come up with states where these two qubits are entangled, meaning their quantum correlations are defined, whereas the individual states may not. So those are all quantum mechanical effects that actually do not have any classical analog. But you need to have a large number of these things. And then this physical system has to be chosen to have long coherence times, meaning the quantum property has to persist. And you should be able to very reliably initialize and measure these systems, these qubits. And then once you have the bits, you need to be able to do logic operations on them. There are single qubit and 2 qubit operations. These are very similar to classical operations, classical logic operations like AND gates or NAND gates or gates. But they have to be coherent in the sense that if the input is a superposition of states, the quantum logic gate has to work on superposition states at the same time. So it has to work coherently over any arbitrary input states that's allowed to enter the system. And then there is the universality theorem that if you can do a certain number of single qubit gates and 2 qubit gates, then there is a theorem that says you can do arbitrary quantum computation using these finite number of gates. Very similar to the classical universality theorem that's known. So these 5 properties that I highlighted in blue is called DiVincenzo criteria, and that David DiVincenzo in 2000 summarized that if you really want to think about a scalable quantum system to implement quantum information processing, you have to make sure that these 5 properties are satisfied. But to me, that is actually a very physicist way of looking at things. When you try to really put together a system, there is another very important element that's missing, which is how to move bits from one location to another. In a classical CMOS architecture, the bit is represented by voltage, and therefore moving a bit from one location to another is actually a very simple thing. You just link them together with a piece of conductor, which is a trivial physical device. Then your bit is actually transported from one location to another. And it is actually the fact that wires are so trivial in CMOS that we can actually build very complicated circuits. Because if you think about the number of devices that are actually in a CMOS transistor, you have 1 layer of transistors and probably a dozen layers of wires. And all circuit designers sit down and do is actually figure out how to connect things together. That's where all the functionality comes from. But at the same time, a piece of metal is a very simple physical device, and it never attracts attention of physicists. But if you think about ways to transport qubits from one location to another, that actually turns out to be an extremely difficult problem to do. Okay? So we actually have to think about transporting qubits between logic gates in a computer, make sure that we can do that very effectively. And that is actually a very important architectural element to try to build large-scale systems. So any proposals for building scalable systems that focus only on these 5, they're great necessary conditions, but they're very far away from being a sufficient condition. So one trick that is widely used is this thing called quantum teleportation. It uses what's called these entangled states to ship qubits from one location to another. And I have a very, again, simple operational definition of what quantum teleportation is. Now, we think about 2 particles, B and C, and they are in entangled state. This is quantum mechanical entangled, meaning that their correlations are extremely well defined, but the individual state of these particles, B and C, are not necessarily well defined at all. But if you come up with this entangled state, they're basically somehow related to each other, you can actually use this as a resource to ship an arbitrary qubit A from this particle to that particle. And the way it works is you bring these 2 particles together, and then you do a joint measurement. Somehow what we call a Bell state measurement. And basically, you let them interact a little bit, and then you make a measurement. And then these 2 guys are now dead quantum mechanically, because you've made a measurement, you collapse the state. And then you extract 2 bits of classical information, and then you send it over to this guy who holds the particle C. And then based on that 2 bits of classical bits of information, that person will do something to this qubit. And voila, shows up this initial state A gets replicated on this particle C. Okay? And that's called a quantum teleportation process. And this actually works for an arbitrary state A, in the sense that if A was also a part of an entangled state that's entangled with another state D, after this teleportation process, you actually have this original state D entangled now with this particle C, and because this state A has been teleported to here. And that is called entanglement swapping. This is a special example of quantum teleportation where the state that you teleport is actually entangled with yet another quantum state. And here, basically, you can create an entanglement between this particle and that particle, although these 2 guys directly have never interacted. Okay? All we had was this guy originally entangled with that, this guy originally entangled with that. Let these 2 guys interact, and then now you can actually transfer the entanglement between these 2 particles. And this is actually a very useful protocol to ship quantum information from one location to another. And one last element I'd like to emphasize is if you really want to build a quantum computer, all of these implementations has to be technologically tractable, in the sense that if we need technologies that we don't have today, then we actually have to start inventing technologies. So technologically tractable means we can actually hopefully make this with technologies that are within our reach today. Okay? All right, so let me briefly emphasize the power of quantum computing. And this is a factoring problem. It is one of the problems that are known where classical computers quantum computers can do exponentially better than classical computers. And here I think about an n-bit number that you're trying to factor, which is very important for encryption techniques. And then here I have a time to factor an n-bit integer. And this is an analysis done by Rod and others in 2005. So in using a classical computer in 2003, that's already 10 years ago, people put together a 104 cluster computer and actually used the best known classical algorithm to factor a number, which is called the number field sieve algorithm. And they factored a 512-bit number. Okay? And that that 512-bit is somewhere here, right? And it took them a few months, a few months to factor that number. And if you take that point, this is a data point here, factoring a 512-bit number. And if you extrapolate how long it takes to factor large numbers using the same kind of algorithm, it actually scales extremely poorly in the sense that in order to factor a 1,000-bit number, it takes about 1 billion years using the computer technology of 2003. Okay? Now, if you are able to construct a quantum computer that can actually solve the same problem using the Shor's algorithm, then this kind of really ugly scaling really becomes a very favorable scaling. And that scaling so this is an assumption of a Shor algorithm running on a quantum computer that runs at 1 hertz. It's a very slow computer. You do 1 logic gate per second. Okay? And then you can see that this 1,000-bit number factoring still takes on the order of 1,000 years. But the scaling is actually not as ugly as this one. Right? Now then they actually considered different kind of computer architectures and see if the improved architectures can make this factoring problem go faster. So here they consider, in this line, they consider a Shor algorithm still running on a quantum computer that runs at 1 hertz, very slow computer. But this now has a NTC stands for nearest, 2-qubit, and concurrent. That means you're only allowed to do 2-qubit operations between qubits that are right next to each other. You can't really do things that are far away. But you're only allowed to use 2-qubit gates and not multi-qubit gates. But you're allowed to use concurrency. Concurrency means you're allowed to run things in parallel. And as the problem size gets bigger, you get somewhere between 2 to 3 orders of magnitude improvement as the problem size increases. And using this, you can actually improve your 1,000 years to maybe 10 years. Okay? And then this lowest line is where they assume that you have a computer hardware architecture that lets you pick any 2 qubits in your computer and then do logic operations between them. Okay? If you're allowed to do that, then you can actually start introducing much more efficient classical analogs of adder and arithmetic algorithms that allows you to speed these things up even further. Okay? And by doing that, you get, again, another 2 or 3 orders of magnitude. Again, still Shor algorithm running at 1 hertz. And this 1,000-bit problem now starts to become a couple-day problem. Okay, so what this means is just by improving the way that your hardware is connected, right, you can actually get somewhere between 4 to 6 orders of magnitude performance improvement. And this is exactly what people do in computer architecture. They try to hook things up in a different way so that certain calculations go a lot faster. And again, there's no quantum enhancement. This is all classical system engineering to get to that point. And of course, if you can run your clock 1 million times faster instead of 1 hertz, if you can produce quantum computers that run at 1 megahertz, then this will improve by 6 orders of magnitude. And now the 1,000-bit factoring problem becomes a 1-second problem. Okay? And very, very optimistic. But here, basically, the idea is between this purple line and this blue line, there is somewhere between 10 to 12 orders of magnitude performance improvement you can do just by doing better engineering. Okay? All right, so some people say, but we're writing Moore's law, so classical computers get exponentially better. So how does that help? And of course, if we assume another 30 years of Moore's law that we can write and improve your classical computer's performance by a factor of 1 million, this line will come down by a factor of 1 million, meaning a 1 billion-year problem will become a 1,000-year problem. But the poor scaling still remains, and by the time you pick a 2,000-bit number, you will still take over the age of the universe to solve it. So this really shows the power of quantum computing, and then the opportunities for doing better system engineering to construct machines that can solve problems faster. So I take that as a motivation to to lead you to an example. So where, in my opinion, where the quantum computing is today is very similar to our classical computers in the 50s, where we have a very promising device, and that was the first transistor. So the basic functionality of a transistor operation has been demonstrated, mostly led by in ion trap quantum computing, people like Chris Monroe, really pioneered all the components of what it takes to demonstrate a logic operation in a single device. But what we're lacking is this integrated circuits technology. How do you put large systems together using all the components in such a way that the cost and performance will improve very fast, basically by a factor of 1 million every 30 years, by constructing the circuits practically the same way we used to do it in 1958 when Kilby and Noyce came up with IC technology. So that integration technology is really what we need to start building systems that are a little bit more complicated than what we have today. So I try to think about the key defining feature of the IC technology that makes it unique, makes it scalable. The first element is that IC technology allows you to integrate all components needed for building a circuit, not just transistors, but transistors, wires, resistors, buses, and all that. And then we also don't randomly put large numbers of bits together or transistors together. We actually design it in a way that after integrating 1 billion transistors, we control each and every one of them and make sure it does what we tell it to do rather than what it wants to do. So this architectural control makes sure that you can control each and every one of them, and the fact that you have to be able to bring all the elements of the system together onto an integrated system, or something that we will have to make sure we replicate as we think about quantum versions of these IC technology. So let's go back and talk about the transistor. What is the element? And here we use the 171 ytterbium hyperfine qubit. Again, ytterbium qubit has been pioneered by Chris Monroe's group over the last 5 or 6 years. And these are the operational elements that I want to highlight so that we can actually take those elements. This is the transistor man version of what it takes to build a quantum transistor device. And all of that is summarized in this paper by Steve Womschenk written in 2007. So here, it's basically an atomic system. You strip an electron out of a ytterbium, and now it has a charge. And now you can actually use some advanced techniques, which I'll come back to later, to trap them in free space. And then you can actually use the 2 hyperfine ground states as the qubit state. This actually has good coherence times. Meaning without trying much, you get on the order of a second coherence time. And if you try to make some effort to shield excess fields and things like that, you can improve that coherence time by another 3 orders of magnitude or so. And then in order to manipulate them, we actually use an optical transition to this upper lying level. And the way you initialize it is you put a resonant light between this upper level and these 3 levels. And you can very effectively optically pump all of these populations down into this ground state. And after scattering only about 10 photons or so, you can actually get many nines of precision in doing that. And again, that's how you initialize these things. And then when you try to detect whether the qubit is in upstate or downstate, at this time you put a resonant light between this level here and this lower level here. And when you do that, this level actually decays into one of these 3 levels. Okay? But the decay from this level to this lower level is actually forbidden by atomic selection rules. So what happens is when the atom is in this state, it actually scatters many, many photons because it will come back down, and it will get repumped, and then it will scatter another photon. So when you look at how much light is being scattered, you actually collect a few photons, several photons on your detector. Whereas if the atom started down here, this excitation light remains far off resonance and nothing happens. So your photon number statistics really go very low. You get either 0, or sometimes you get 1 click based on the dark count of your detector. So basically the way you do state detection is you shine a laser beam onto this atom and see if it glows. If it glows, if you collect enough photons, you call it bright, and that's a spin up state. And if it doesn't glow, then it's a down state. Okay, so again, trap an atom, shine a laser beam, look at it. That's what we need to do. Now, the next step is we have this qubit down here. So can you do single qubit gate? In classical computation, a single bit gate is either an identity gate or a NOT gate, where you flip the state. In quantum mechanics, there is actually an infinite number of gates you can do, coherent rotation of these two states, which can either be done by direct microwave transition, by shining microwave on them, or we can do that by using an optical transition, taking two laser beams, whose frequency difference exactly matches this energy difference. And then with that, you can actually induce transitions between these two levels, which is basically the formation of your single qubit gate. And again, this work was all pioneered at here at the University of Maryland in Chris Monroe's group. It turns out that if you use this 355 nanometers, there is a very, very cost-effective laser source to do this extremely well. Okay? So that's how you manipulate single qubit states. And then the next tricky one is what do you do when two qubits have to interact with each other? That means you have two qubits, and I want to flip the state of this qubit based on the state of the other one. And that's called the control NOT gate, which is known to be a universal gate. And in order to do that, that's a little bit tricky, so I'm just going to wave my hands and tell you how to do it. So when these ions are actually trapped in a harmonic potential, because in free space, the motional center of mass motion, the motional degrees of freedom actually are also quantized. And these motional excitations actually form these subbands with respect to the spin state. So the atom can be in down state, but it can also be in motional ground state versus a single excited state and two excited state and so on and so forth. So what you do here is you tune these lasers in such a way that you induce a transition between the spin down state and spin up state, but we do it in a way that you also excite one motional state as you flip the spin. Okay, so you detune this laser in such a way that I go from this guy, which is motional ground state and spin down, to motional n equal 1 state and spin up. Okay, when you do that, what that means is if my atom is in the ground state, then I can actually flip the spin, and then I can excite one of the phonon modes. Okay, I can excite one excitation in the center of mass motion. But if I started up here, right, then this resonant beam will actually flip the spin and want to go to n equal minus 1 state, which does not exist. Okay? And therefore, when the spin is up, nothing happens. So when your spin is down, you flip the spin and you excite one motional quanta. But when the spin is up, nothing happens. Okay? So you can actually conditionally excite this one motional quanta depending on the state of your spin. Okay? Now, instead of having one ion in this trap, if you had two ions in the trap, the motional mode is actually shared by both ions. So you can actually excite this one motional mode based on the state of one qubit. And then you can actually do the reverse onto the other spin. If the motion is excited, then you flip it. If the motion is not excited, you don't flip it. Now, if you do that, then if the first one was in the spin up state, then nothing happens because you never excite any motion. But if the first one is spin down, then you excite a motion, and then this guy gets flipped. And therefore, roughly speaking, you can actually induce a conditional spin flip depending on the state of the other one. And that's how that's basically the physical, very intuitive physical process of how that's done. There are many, many versions of that, which makes the process a lot more robust. And again, it was demonstrated in Chris's group. But basically, both single qubit and two qubit gates, again, the operational mechanism is you basically shine laser beams, carefully tailored laser beams. And then you can actually induce single and two qubit gates. So if you think about this, I want to trap a fairly large number of ions. And then I want to be able to selectively shine laser beams on them. And I want to be able to look at them, meaning detect the fluorescence from these atoms. And those are the procedures that we need to know in order to engineer a bigger system. All right, so with all these physics in mind, let me actually briefly think about, describe how ions are actually trapped. So this is what's known as the RF Paul trap. And a Paul trap, the nice thing about ions is it has the atom itself is charged, and therefore you can use the charge as a knob to actually trap the particle. But what's known is because the divergence of electric field has to be 0, you can't really never create a static minimum in potential in free space, in three-dimensional free space for an atom. What you can do is you can create a saddle potential. If you create a quadruple null in a free space, then you have a saddle potential where the electric field is confining in one direction, but it is actually not confining in the other. And the ion will actually like to escape through that channel. But then if you, instead of applying a static field, if you apply an RF field and flip this field potential up and down very quickly, then the ion will actually see trapping potential in all three dimensions. And that's how you create a electrostatic trap or RF Paul trap. So typically, the goal is to create this quadruple null by saying, for example, one way to do it is create 4 poles, 4 rods, and then ground 2 of them, and then apply RF to the other 2. And then in the middle of this line, you actually have a linear potential trap. And then you can further confine the potential in the longitudinal direction by segmenting these ground electrodes. These are RF grounds, but I can actually segment them and then apply positive voltages to these gray electrodes and lower voltage in this white electrode, and then I can actually further create potential in this third dimension. And then I have a 3-dimensional trap. So that's how people used to make ion traps, using literally 4 wires or 4 rods, or people still do that, but Chris has the 4 blades that look very much like this. But then you can also map this kind of a 4-rod structure into more planar structures. This is an example of a trap that was built in Dave Weiland's group, where they start with sapphire substrates, and then they evaporate gold and metallize gold. And then you can actually use this 1 and 1 prime here as RF electrodes, and these 2, 3, and 4, and 2 prime, 3 prime, and 4 prime as the RF ground and DC electrodes to actually map this structure onto something that is a little bit more manufacturable. But these devices are still hand-assembled, and they can make multi-segment traps this way. But by the time you want to go to very large numbers of segments, then you really can't do it this way. We have to really go to microfabrication techniques. But anyways, in this type of trap, people have trapped multiple ions in a chain. I think Chris's group can do up to 18 chains today, 18 ion chains. And what Chris and Lu-Ming Duan's group have shown many years ago is you can, once you have a long chain, let's make sure that we dedicate some ions up here to make sure that these ions are not moving too fast, meaning you can cool them down. And once the motion is reasonably manageable, what they do is think about laser beams that can point to certain ions. And then by shining laser beams, you can start moving the ions. You can excite the lateral motion. And because all these ions are charge coupled, when you shake one, the other one starts shaking too. And then when they are shaking in just the right way, I can shine another laser beam onto the other ion and then absorb that motional state into the internal spin state, just like the simple model I showed you about. So if they have 2 laser beams that they can independently steer to select 2 ions that they can shine on, and if they can actually pulse them with some appropriate sequence of pulses, you can actually do arbitrary 2 cubic gate between any 2 ions that you select. So this is what we call an elementary logic unit. This is actually a chain of ions within which we can assume we'll do arbitrary quantum computation between them. Okay? The requirement, we need a long chain. And we need 2 laser beams that we can independently steer and select 2 ions that we can hit. And then we actually have to design our pulses to hit them just the right way. And I think other than these steerable beams, all of these protocols are currently under development in Chris's lab. Now, the next step, again, you see Monroe in all of these papers, because he's really pioneered in many of these protocols. So in my mind, he's the transistor man. So the next step is you can start to think about making very complicated trap structures where there are some RF rails that really trap them, and then you can actually have many electrodes of DC where I can actually create potential to trap a chain of ions here, create a potential to chain of ions here, and here. And if I wanted to do 2 cubic gate between these, I actually shine laser beams and do it. But if I wanted to do 2 cubic gate between, say, this ion here and that ion there, then I can actually pull this ion out and then move it over here, merge them into this chain, and then I can do the 2 qubit operation. And people have demonstrated the shuttling of ions, moving them around, merging and separating from multiple chains. This kind of operation can actually be done. I'll show you an example of how that's done. So by doing that, so this is a cartoon of how to create these ions and then make them fly around. And then once they are together, you can actually shine laser beams to to do multi-qubit operations. And people have, this is again, Dave Weiland's group, they made a much more complicated trap. Again, these are, as you can see, all hand-wired and wire bonded, and all the filters are soldered in here and so on and so forth. But this actually has on the order of a couple dozen electrodes, and then they have this cross structure where they can actually shuttle ions between the zones here and zones over there in a free way. So this kind of technology has very well been demonstrated. And this, you can imagine that if I have multiple chains on a chip, I can move things around and hook all the chains up together and do arbitrary operation between all the chains on a chip. All right, so that's fairly scalable. Now we're talking about, let's say we talk about 10 ions in a chain. We're talking about maybe a dozen chains on a chip. So we're up to maybe 100 qubits that we can potentially do. But it's hard to think about making this chip really big. It's hard to think about making chips that are meters on a side. So there will be some limitation on how many ions you can put on a trap. So on a chip, and therefore the next step is to think about how to connect these chips together and try to make a network of these processors that are connected with each other. So the way you do that, again, if you see here, it's Duan and Monroe again. Here, basically, the idea is you create a atomic state that is in a superposition state of these two ground states here. That's an example. And then you excite these two ground states up here by using a short pulse laser. And that will take this upper state to the lower level, and then the lower level to the upper state. And they remain two independent two-level systems because of atomic selection rules. So that this superposition here will actually now be transferred to the superposition up there. And then you let this guy decay. And these two states can actually decay into these channels. But they can also come down straight. We can actually filter out the polarization of the photons that decay into these two channels and let these guys come straight down and select only the ones where they come down. And then what happens is the energy level up here will only decay down to the lower level here. And the energy level down here will only decay down to this upper level here. And therefore, the color of the photon that's emitted is now actually entangled with the state of the ion. Okay, so again, the message here is you can excite the atom in such a way that it spits out a photon, but the degree of freedom of a photon, say the color of the photon, is now entangled with the final state of the atom. So I can actually create an ion-photon entanglement this way. Okay, and that's actually work done again in Chris's group by Boris Bulinov. But if I have an ion and a photon that's entangled, I can set up another setup on the other side, identical setup where an ion and a photon emitted by this ion, they're now entangled. And I can actually interfere these two photons. And in my formal language, this B and C, this photon and this ion is entangled. This A and D, this photon and this ion is entangled. But I'm actually interfering these two photons and do this correlated measurement. And when I do that, I can actually take this photon state A and then map it and teleport that onto the ion state here, using this ion-photon as the entangled pair. When I do that, I can start with two ion-photon entangled pairs and then actually create entanglement between two ions that are sitting far away. And this actually work was done by Dave Moring in Chris's group in 2007. And this is an example of actually creating two ions that are separated with each other. They're actually emitting photons. By interfering the photons, you can create entanglement between the ions. So I can actually make entanglement between two ions that actually never interacted. These two ions may sit in two different chips. They may be sitting tens of kilometers away. But if I have a way to exchange photons, send two photons and let them interfere, then I can actually create an entangled pair between these two ions. And then in 1999, Gottesman and Chuang came up with this protocol. Say I have a particle A here and alpha here and a beta here, and I want to do a C0 operation between these two. But say there is a big separation between these two guys, and I really can't bring this particle to interact directly with that guy. But if there is an entangled pair that's shared between this site and that site, and I'm allowed to do local operations between one of the entangled pairs with alpha and the other one with beta, then just by doing measurement and classical communication and single qubit operations, I can actually do C0 operation between a particle here and a particle here. Okay, so long story short, if I have a chain of ions here, I want to do a C0 operation between this ion here and that ion over there. but I don't have a way to bring them together and make them interact directly. What I can do is identify two other ions between which I can create entanglement by this photon interference protocol. And when these two guys are entangled, I can use that as a resource to do a CNOT operation between this ion and that ion. Okay? And that's a way to take two ions that are separated by long distances and then doing multiple qubit operations between them. All right, so I think my transistor man explanation is done. It's very complicated. Instead of one transistor, I have lots and lots of protocols. But from here, we can actually now talk about systems that we can build. Okay? All right, so this is actually the heart of our music project collaboration, which is a multi-tier approach to scalability. So again, this is a little hard to see. But imagine a long chain of ions. And I have some individual addressing system that allows me to point laser beams to individual ions in the chain. And then one of the ions here is actually now interfacing to an optical interface. And this optical interface, let's see what's going on here. There we go. This optical interface is where the photon spit that this ion emits is effectively, very efficiently coupled into a single mode fiber that I can take somewhere and use it as an optical port. Okay? So this is my elementary logic unit. Again, long chain of ions within which I can do arbitrary computation, and one optical interface that allows you to create photons that are entangled with this interface ion, which I call the optical port. And then the next step is I'm going to build a fairly large number of these things. So each one of these red boxes is a chain of ions where you can do arbitrary quantum computation among them. And then one optical interface that can actually collect photons that are entangled with only the ions. And then I can actually connect them up into a optical cross-connect switch. And this switch, I will explain, is N input ports and N output ports, where any input port can be connected to any output port. Okay? Just by reconfiguring the internal mechanism of the switch. And then on the output port, on the output side, I have a pairwise interferometer. So port number 1 and port number 2 will actually interfere and go to 2 detectors. Port number 3 and 4 will do that, and so on. So here I have N input, N ELUs connected to this thing on the input, and N over 2 interferometers located on the output port. And if I want to create a perform a CNOT gate between a qubit on this unit 1 and unit 16, what I do is I configure this switch in such a way that the optical port from unit number 1 is connected to output number 1. Here, the optical port from unit number 16 is connected to output number 2, so that the photons from these two guys can interfere. And I start this protocol where I try to emit photons. And when the photons do interfere, then I've created an entangled pair between a qubit on this unit and qubit on that unit. And I can use that as a resource using local operations and perform two qubit gate between qubit 1 and qubit 2. Okay? So this is a way that I can create a large number of small units that are globally connected. And on top of that, I can actually pick arbitrary qubits in my entire computer and do two qubit operations between them without paying any extra distance-dependent penalty. Okay, so this actually allows you to realize that abstract concurrent architecture where I'm allowed to do a 2 qubit operation between any pair of ions in my system. All right, so this is how we feel we can actually scale our quantum computer. And I'm going to explain all of the components technologies that are needed to realize this in the remaining time. Now, the other thing that we can do is this kind of entanglement distribution can be performed over 2 units that are separated much further away. So in this example, I have a unit here which holds my chain of ions. And one of the optical port spits out photon to the right. Another port spits out photon to the left. And here I have the same thing, which spits out a photon to the left. And I take a photon from here and a photon here from here and then interfere them. And when that's successful, then I create an entangled pair between an ion here and an ion here. At the same time, I can actually run the next chain in parallel, create an entangled pair between here and here. Now I have 2 entangled pairs of ions that are generated between these 2 links and those 2 links. And these links can, in principle, be many tens of kilometers away. Now once that's established, then I can actually take these two qubits that are here, one connected to this side, the other connected to this side, and teleport one of these qubits to over here using, using this pair as a resource. And by doing that, I can actually now double the distance over which entanglement is distributed. And when I do this in a nested way, I can actually reach arbitrarily long distances without paying the exponential penalty of photon loss. So this is actually called the quantum repeater protocol. It's been known since 1998. But I feel that finally we have all the pieces necessary to actually construct this thing. At the node of a repeater, we actually have a communication qubits that are coupled where the photon is emitted effectively into a single mode fiber. But the photon that ion typically spits out is in the visible UV, and it really doesn't propagate very far. So what we are planning to do is use nonlinear optical process to convert the wavelengths of this blue photon into something that's more amenable to long distance propagation, like a telecom wavelength. And then you can actually let this, and then if you couple that into a single mode fiber, telecommunications fiber, then we can actually let these photons propagate long distances before they interact. So you can actually create, by using this, inserting this wavelength conversion process, you can really generate entangled ions that are separated by many tens of kilometers, which forms the basis of entanglement distribution over long distances. And this is a little cartoon of the technologies that we feel we can realize this type of a system. All right, so with all that vision, let's see what it takes to the technology pieces that are needed to build them. Okay. First one is this ion trap chip. So I showed you the full rod trap, and then how people can actually make that into a hand-assembled structure that is slightly more complicated. But when you want to think about these very large-scale chips, then we need a lot more complexity to build this. So in 2005, John Chiaverini in Dave Wineland's group realized that you can actually take this full rod trap and conformally map the electrode structures onto a plane, onto a pure plane. And then I think Dick Slusher and I led a little study group at labs, and we quickly realized that if you can do that, then we should really use silicon microfabrication processes to build these things. And then a lot of activities of trap fabrication have started at NIST, Georgia Tech, Sandia, MIT, and a bunch of other groups in Europe. And then people started using them to demonstrate the viability of this approach. And these are some of the advanced traps that were developed under our collaboration under this music project. You can see that we can actually make traps that are in the geometry of a ring. They can do these junctions, and in which your ions can move back and forth, any one of these three arms. And then you can actually put them together in a more complicated structure like rings and chains. And then we can also integrate optical elements like mirrors and things like that into the trap structure. And with these technologies, the traps actually come to us in a package like this. Again, this is a picture that you've probably seen a lot here in Maryland. But this is how the traps are actually delivered to us. So one of the criticisms for ion trap quantum computing was it's not very scalable. Atomic physics, you can't think of doing atomic physics on a chip. And our claim is that's because we've never invented the technology to do it. And here is an example of how we do it. And the way we do it is, let's say I want 7 ions on a chain, and I want to make that. I tell our collaborators at Georgia Tech or Sandia, this is what I want. They'll go back and they sit on a CAD tool and design the trap. They go send it to the fab and fabricate it. And then they package it like this, just like any other silicon chip that you would buy, and then it comes to us. And then we stick it into a chamber. And this is an example of what we can do. This is from my colleague Jason Amini at GTRI. So what he's doing is here they have a loading zone where they're actually loading individual calcium ions in this case. And whenever he loads an ion, he actually changes the voltages on this complicated chip and then shuttles the ion over here. Okay? And then he can actually trap and shuttle and trap and shuttle and start to build an ion chain over here one by one, exactly the way we prescribe them. So starting to think about hardware systems where ions are actually loaded one by one and building chains that we want is actually a pretty real technology today. All right, so these surface traps are attractive because you can actually make very complicated structures, but there are some key questions that still remain. They're still a very young technology. The first question is, can you trap ions for long enough? Because these surface traps tend to be much shallower than these macroscopic traps. So can you hold ions long enough? Can you make sure that you can bring all the laser beams that's necessary to actually interact with the ion without hurting the traps? And ion heating is basically the motional state of the ion really cannot change while we're doing these 2-qubit operations. Can you make sure that this motional change, the rate at which this motional states change, is small enough to ensure that we can actually do useful operations? And then the answer to that question that was everybody was pursuing over the last few years. So many of the experiments that we've done at Duke confirms that all of these things can actually be implemented in surface traps. And the performance is actually comparable to large-scale systems. So the experiments here is actually somewhat boring in the sense that we did everything that Chris can do, but on a surface trap. So I'm not going to try to spend too much time talking about that. But there are some catches. If you think about traditional circuits that you take these macroscopic pieces and wire and solder it down onto a PCB, you can do it in your lab, and they work because these things are big, right? But when you try to make these circuit elements on a microfabricated facility, because the features are so small, a piece of dirt can actually short them, right? So we actually had to invent clean room technology to make microfabricated circuits work reliably. If you do that, they're very reliable. Okay? But same thing here. If you have these microfabricated traps, and if you handle it just like any other macroscopic trap, the chances are something will go wrong. So we actually have to make sure that our optics and our handling of these traps are compatible with these microfabricated traps. And that's kind of what we have paid a lot of attention to. We have these, we built these chambers that have good pumping properties. And then we handle all of our vacuum work in the clean room because our chip traps have to be operated in a clean room in order for them not to fail. And if you do that, we get really good pressures. And we get really long trapping lifetimes, very comparable to macroscopic traps. And we can actually trap these ions in these microfabricated traps in a very reliable way. We've actually tried 4 traps from Sandia National Labs that were delivered to us. Every one of them worked exactly as they should in pretty much the first try. So we can actually say that if we handle them correctly, these technologies really work and they're reliable. Now the rest of it is just showing that we can do reasonably good single qubit gates. We can actually do pretty long coherence times. Again, coherence times of like 1 second can be measured. We could actually manipulate its motional states. And then we can actually measure the heating rates. This heating rate is if you have an ion trapped, if you're not cooling it, eventually it will actually absorb energy from the trapping environment, and then the motional state will change. We can actually show that this heating rate is on the order of a fraction of a quanta per millisecond. Again, all these numbers basically mean that surface traps work pretty much as well as macroscopic traps if you make them right and if you use them right. Okay, so I think that's one of the main discoveries over the last few years. Is these kind of fabricated traps that are fancy can actually work very well if you treat them right. All right, so all of that I skipped because the data is actually not very exciting, but we actually nevertheless had to go make sure that it can be done. But for the system integration, the trap, just making trap and being able to trap on it is not sufficient. First of all, it actually has more requirements. It has to be able to support all trapping functions, including multiple species of ions, and then shuttling them between chains. But we also have to provide optical access for all of these laser beams that has to come in. And it turns out that these optical beams, we need a very large number of them. This is schematic of a ion trap with a trapping axis. And then you have to bring in laser beams from the top. We have to bring laser beams from the side. And they all have to be pretty well focused so that we can actually hit individual atoms. And when you put all these requirements together, the trap is not a trap. The trap actually has to be designed so that it actually is compatible with all the driver requirement and the optical interface requirements. So after a couple of years of looking at all the issues, we've actually realized that the trap geometry really can't be independently defined. It actually has to be designed and fabricated in the context of an optical system. So this is an example of our collaboration with Sandia. First of all, I want to bring in the laser beam from the top, but I want to focus this beam really tight so I can actually hit individual atoms that are separated by a few microns. That means I need a large numerical optical access, large numerical aperture optical access. So we actually have to drill a hole in the middle so that the beams can come here, and then after they hit the atom, they can actually diverge. Okay? The other challenge is we need to bring in these beams that are skimming through the surface. And the ion sits only about 70 microns or so above the atomic the surface. And therefore, if you want to bring in a reasonably tight beam, they will start to diverge. So you can't really, if the chip is very large laterally, then you can't really bring in the beam that are reasonably well focused. So this is an example of what we ended up doing is we tried to reduce the width of this trap so that optical access from the sides can actually be accommodated. So this is actually our latest and greatest trap that was just delivered to us about a few weeks ago, which we were able to trap in this just last week, and we're trying to make sure that they can be integrated for all of these optical addressing functionalities that we want to achieve. Now the next question is, what about this optical cross-connect switch? Now that can actually be constructed. I mean, a lot of companies were putting in a lot of development dollars in the heydays of telecom in the late 90s and early 2000s because there was a need for very large port count optical cross-connect switches. And so people were thinking about making large arrays of fibers. Half of them are being used as optical inputs, and half of them are being used as optical outputs. And then you would collimate the beams using micro lenses and hit them onto a tiltable MEMS mirror. And then these small micro mirrors will tilt and steer the beams to the output that you want. And then we can make a very large scale input and output optical switch. And that indeed can be done. We actually developed these MEMS mirrors. A lot of them were actually developed by my colleague Vladimir Kshuk, who's now at NIST, went through University of Maryland. These devices were designed by my MEMS development colleagues. And we can actually make very large numbers of these mirrors. So here, using surface micromachining technique, we've created the 256 mirrors. And using a bulk micromachining, we've actually created 1,296 mirrors. And then we can build optical switches that look like this. And they actually, in this case, it has a 256 optical inputs and 256 optical outputs. There are 56,000 possible connections you can actually make in a 238 by 238 configuration. If it's all 256, there are 65,000 connections you can make. We can actually make individual connections, measure throughput on all of them, and then look at the average and loss and its distribution, which is reasonably tight. Turns out all of these main losses are coming from the AR coatings of our optical coatings. And then the big chunk of the variation really comes from the connectors themselves. So that basically means we can build these optical systems where 56,000 single mode imaging is done between cores of input fibers and output fibers can actually be done very well with worst case 6% transmission. And then the next question is, can you make an even bigger switch? And this is actually a version of 1296 inputs and 1296 outputs. That's me about 10 years younger. Here, the mirrors are 1296 mirrors. They come in a package that's about 6 inches on the side. This is a ceramic package that's the size of a bathroom tile. And inside here, we have bundles of fibers. There are 2,600 fibers in here and 2,600 fiber connectors. And there's over 5 kilometers of fiber in this little box, just for the mere density of it. And then we went ahead and measured all 1.7 million possible connections. Initially, we anticipated that would take many years to do it, but we figured out how to engineer a system so we can do this in half a day. And then this is a plot of all, in this case, about 1.4 million possible connections we can make in this switch. And this really is a functional 1100 by 1100 optical cross-connect switch. So big optical switches with thousands of ports. It's not just possible, it does exist. Okay? All right, and then the last question is, the next step is how do you create this beam steering systems that can actually do individual addressing of atoms? Traditionally, these beam steering can be done using either acousto-optic or electro-optic deflectors. But there are some issues with scalability. It's hard to do multiple beams in the same spot. So we actually tried to use this steering mirror technology, tilting mirror technology to do the same thing. They actually are very scalable and low loss over multiple bands, but there are challenges. These optical switches I showed you based on tilting mirrors, it takes milliseconds to tilt them. But for these atomic physics, we really want them to tilt in microsecond time scale. So we had to make these mirrors move 1,000 times faster, which is mechanically things moving at roughly megahertz is really not very easy to do. But nevertheless, we can actually optimize the system to do that. This is a simple example of how a single beam coming in can actually bounce around. And I have two mirrors, one tilting in X direction, the other tilting in Y direction. And the beam coming out can now steer in 2 dimensions. The beautiful thing about MEMS is I can actually use the same system, but instead of using 2 mirrors, I can use 4 mirrors and steer 2 beams simultaneously. We could actually scale this up to large numbers of beams that you can simultaneously steer. We've actually constructed up to systems with up to 6 beams that are being independently steered. And then with that, you can actually create systems where I can take 2 different colors of beams and then steer them independently over a fairly large area. And you can imagine I can use this to direct individual atoms in my chain of ions. You can see that the beam profile is very, very nice and clean. And then we can actually do this switching over on the order of 5 microsecond kind of time scales, a fraction of less than 5 microsecond time scales. So now we actually took this guy, and our collaborators at the University of Wisconsin, Mark Safman's group, they actually have neutral atoms they can trap in 5-site chain. And then we can actually put their addressing beam into one of these atoms and then induce ground state single qubit operations on them. And this is an example of where I'm pointing my beam to the second atom here and then inducing these ground state Rabi oscillations, which is a single qubit gate, and making sure that the 2 neighboring sites, site 0 and site 2, really does not see any light. And then I can steer that beam to my second site 2, which is the one in the middle, make sure that the first and the third one does not rotate. And then I can steer it all the way to the last one at the edge and induce single qubit operations and make sure that the site 3 doesn't see anything. So we could actually apply this MEMS technology to a chain of atoms in this case with time scales on the order of 5 to 10 microseconds. We actually currently have built a system that will do this for the UV. Again, these mirrors are made out of MEMS technology using a foundry process. And then we can actually create these very nice profile beams of focus down to about 3 micron diameter. And we can actually, our plan is to throw these beams onto a chain of ions that are nominally about 5 microns apart. All right, so individual addressing of multiple beams on a chain is something that I think we are very, very close to being able to do. And then the last is how do we improve the optical interface. And this protocol of the atoms emitting 2 photons interfering to create entanglement, that protocol is actually a very low success probability protocol. So this is actually a number from the experiment from Chris's lab. Probably you worked on this. And here the issue is, we try an experiment, and if it doesn't succeed, then we have to start over. But the probability of that experiment, single experiment succeeding is 1 out of about 10 million tries. Okay? So it takes a long time to make this work. And the main reason is that the probability for us to collect the photon into a single mode fiber and detect it with a detector, these efficiencies are really low. So we really have to do some better optics to make improvement over this. So what we went ahead and do with collaboration with Chris's group is we designed this very high numerical aperture lens that are aberration corrected very well. That actually has the ability to collect about 10% of solid angle, whereas in the past he was only collecting 2%. That's a factor of 5. But you actually have to apply this to both sides of the system, so your improvement actually squares. And then this is designed to have much lower aberration, so the coupling efficiency in the single mode fiber should actually be very close to about 80% or so. So we expect to see about a factor 4 improvement in fiber coupling efficiency. Again, when you square that, that's a factor of 16 improvement. And then instead of using 2 detectors, if you use 4 detectors, you can actually improve this by another factor 4. So these just by switching to better optics, you can actually improve this collection efficiency and success probability of that experiment by about somewhere between 2.5 to 3 orders of magnitude. And I think that experiment is currently underway. Making sure that these 3 improvements are implemented. And that would actually make sure that the success probability, which is 1 out of 10 million tries, and you get to try about 1 million times a second, so it's actually not that bad. Every 10 seconds you get an event. But by doing these improvements, we want to see a success every maybe 10 milliseconds by improving it by somewhere between 2 to 3 orders of magnitude. One last way to do this is to really try and integrate an optical cavity with an ion trap. And we're actually currently working on experiments to do that. These are some of the cavity QED parameters. If we do that, successfully we can demonstrate a cavity integrated with an ion trap. We believe about 30% collection efficiency into a single mode fiber is realistic. And by the time you get to 30% collection, I think there isn't much more you can do. I mean, the best you can do is another factor of 3 and get to 100%. All right, so these experiments are currently underway at both at Duke and at Sandia National Labs. All right, so these are some of the technological components. I really need to wrap up. But if you think about the platform for doing a scalable quantum computation or quantum communication, we really don't have a good way. We've actually invented a lot of techniques for making silicon circuits scalable, but we've never invented a lot of technology for making ion trap quantum computing scalable. But it is a technology that one can invent if you understand the problem and think about what is available today. So I say there's a lot of enabling technology that we're currently developing, and those are these microfabricated traps, UHV integration technologies, and all these MEMS and other photonic integration technologies. These are actually enabling technologies that are reasonably available today. Hopefully I've convinced you that all of these things can actually be done today in a reasonable way. And then using these enabling technologies, we just have to design the right qubit hardware. For example, a chain of ions on which you can do arbitrary quantum computation. And then eventually integrate your system to make sure that all of these functionalities can actually be performed. And that is what I call a qubit hardware. Using these new technologies, we can build them. And this is actually, these two are what I call the hardware aspect of quantum computer. But if you think about what it takes to use a classical computer, just the hardware chips is not enough. In order for you to use it, we need much more than that. So if you think about what it takes to run this thing, this classical computer, quantum computer, you actually need a lot of laser systems. You need beam delivery systems, and you need a bunch of electronic controllers to actually tailor that provide you the knobs with which you can control these quantum systems. So there's got to be a control hardware. And then these actually have to be controlled some way. So we have a lot of digital circuits that we actually custom build and integrate. And then we have to think about, this is basically similar to the operating system of a classical computer, where all of the control hardware and its software interfaces have to be provided in a systematic way. And that's what I would call the firmware side of quantum computer. Based on top of this quantum hardware, you really need a classical digital hardware to really drive this whole thing. Now that will give you all the hardware, but when you think about a quantum algorithm, it turns out that there's a lot more that you have to worry about. For example, you have to take a quantum algorithm and turn it into basic logic gates that you know how to perform, and that's basically compiling. So when you do a programming, you do a pretty high-level programming, and then compiler actually compiles them into something that operations that your processor can actually execute. It turns out that once you come into these logical circuits, there is an error correction and fault tolerance schemes that are absolutely necessary in quantum computing, and therefore translating the logical circuit into physical gates or instructions that your hardware has to execute requires another level of translation. In this case, it's mostly due to error correcting codes. But once you actually have these physical operations, these are sequence of instructions that your hardware has to execute. Once that's done, then you can actually map that onto your hardware and really schedule these gate executions. And when you do that, you can actually do a pretty rigorous resource and performance and error estimations. And really, you need all of these layers to make a quantum computer work. And this is a highly integrable technology. And this kind of, all of this compiling, assembling, and scheduling is what I call the software aspect of quantum computing. And you really need to have all of these elements to really realize a quantum computer. So our current music program actually covers a very large range of hardware, firmware, and software development. And we actually have some other high-level programs to really look at the procedure of taking the algorithm and this is really a computer science kind of approach to take a quantum algorithm and turn it into physical operations that can actually be mapped onto physical hardware. But this is what it takes to get the quantum computing going. So this obviously can't be done alone. It's a fairly large collaborative effort. This is my team at Duke. And I also have many collaborators, including Chris here, that's working on this realization of the music. On Spark, the quantum communication, we have collaborators from Harvard, Stanford, Yale, Waterloo, and Element 6 on top of Chris and others here. So I have to acknowledge a bunch of other collaborators we have in making sure that all of these hardware can actually be realized. And I'd like to thank our sponsors for enabling our work. And thank you for your attention.